All right, so let's jump right in. You hear it all the time, right? AI is getting incredibly powerful, but there's this catch. The best ones, the most powerful models, are often complete mysteries. We call them black boxes for a reason. You put something in, you get something out, but what happens inside? Who knows? Well, today, we're going to pry that box open.
And this quote, it just nails the problem perfectly. It's what people in the field call the AI black box paradox. It's this weird trade-off. The better a model gets at its job, the more accurate it is, the harder it is for us to understand how it's doing it. Think about things like deep neural networks. They give us these mind-blowing results, but we completely lose the why behind the what.
Which leads to the huge question. How can we ever really trust them? And this isn't some academic debate. We're talking about AI making massive decisions in things like medicine, who gets a loan, even in our justice system. You can't just cross your fingers and hope the black box is right. You need trust, you need to know it's being fair, and you have to be sure it's safe. It all starts with understanding. Okay, so if we're going to solve this, we've got to get on the same page with our language. You'll hear two words thrown around a lot, interpretability and explainability. People kind of use them as if they're the same thing, but they're not. And that little difference, it's actually super important for cracking open that black box.
So let's break it down. Think of interpretability as being able to predict the what. So with a loan model, you'd know that, hey, if I bump up this person's salary in the data, their chance of getting approved goes up. You can predict the behavior. Explainability, on the other hand, is all about understanding the why. It's knowing the model approved the loan because it learned that salary and how long someone's been at their job are really strong indicators of a good loan based on all the past data it's seen. So one's about predicting the action, the other is about understanding the reason.
And here's a really key point. This whole interpretability thing isn't just, on or off. It's a spectrum. Way over on one end, you've got what we call glass box models. Think of a simple formula like linear regression. It's totally transparent. You can see exactly how every piece influences the final answer. But then, way over on the other end, you have the deep neural networks we talked about, these incredibly complex systems that are complete black boxes. And of course, most models fall somewhere in the middle.
All right, so we've defined the problem, we've got our key terms down, so what's the solution? How do we actually get inside these things and figure them out? Well, it turns out there are two main approaches people take.
So on one hand, you have model-specific methods. These are kind of like the special tools that come with a specific car engine. They're designed just for that simple, transparent model. They work great, but only for that one thing. Then you have the more powerful approach, model-agnostic methods. Think of these as a master mechanics toolkit. They're universal. You can use them on any model. It doesn't matter how complicated it is. They let us peek under the hood of even the most hardcore black boxes.
Let's actually look at one of these model-agnostic techniques because it's so cool. It's super powerful, but what's amazing is how simple the core idea is. It all comes down to asking one very simple question.
That's the question right there. What happens if we just shuffle one feature? This is the big idea behind a technique called permutation feature importance. You literally take one column of your data, a feature, let's say it's customer age or the daily temperature, and you just mix it all up. You scramble it. And then you see what that does to the model's performance. Okay, so here's how it works, step by step. First, you get a baseline. You measure how accurate your model is to start with. Step 2, you pick just one feature, one column of data, like customer age, and you randomly shuffle the values. This totally breaks the relationship between age and whatever you're trying to predict. Then, step 3, you measure the model's accuracy again. Now here's the magic. If the model's error rate suddenly goes way up, what does that tell you? It tells you the model was depending a lot on that customer age feature you just broke. So that increase in error, that's how we measure how important that feature is. Simple, but so clever.
But, and this is a really big but, all these clever techniques, all this cool stuff for opening the black box, none of it matters one bit if you don't have a solid foundation. And in the world of AI, that foundation is one thing and one thing only, the data.
I love this pyramid because it shows it so clearly. Everybody gets excited about the top of the pyramid. The fancy AI, the deep learning, that's the fun stuff. But you can't build a pyramid from the top down. You have to start at the bottom with collecting data, moving it, cleaning it, getting it ready. It's that old saying, garbage in, garbage out. If your data is a mess, your model will be a mess. And trying to explain a garbage model, well, that's just putting a pretty label on garbage. And a huge piece of that foundational data work is really knowing your variables. You've got your core variables,
These are the main event, like a patient's symptoms. Then you've got related variables, things that might be influencing the outcome, like their diet or exercise habits. And of course, time-related stuff, like when they were diagnosed. If you don't understand the difference, your model can get totally confused and draw the wrong conclusions. Getting this right is the difference between building a solid AI and building a house of cards that's going to fall over.
Okay, now for my favorite part. This is where we take all these kind of abstract ideas and make them real. Let's look at how visualization lets us actually see how these machines are thinking.
This is it. This is the payoff. This chart right here is what you get from a technique like the one we just talked about, permutation feature importance. So we've got a model that predicts how many bikes will be rented on a given day. And just by looking at this, you can see, bam, temperature is the #1 thing the model cares about, followed by the season, whether it's a holiday, and so on. See? It's not a black box anymore. It's a simple ranked list. We're literally looking at the model's priorities.
And believe it or not, it gets even cooler than this. We're not just limited to static pictures anymore. There are these incredible interactive tools now that let data scientists basically play with the model in real time. They can tweak an input here, change a variable there, and watch how the model's decision-making process changes on the fly. It's less like looking at a chart and more like having a live conversation with the AI itself. This quote is just perfect, isn't it? ML is great until you have to explain it. It really gets to the heart of everything we've been talking about. The power of machine learning is amazing, for sure, but that power is only truly useful when we can turn around and explain its decisions to the real people whose lives are impacted. And these techniques, these are the tools that let us do that. So I'll just leave you with this final thought. AI is weaving itself into every corner of our lives, right? It's making decisions about our health, our finances, our futures. And as that happens, the most important feature we need to build into these systems, it's not more power, it's not more speed, it's the ability for us to always be able to stop and ask one simple 3-letter word: why?